3:47 a.m. inside an aerospace testing lab. A senior engineer watches her latest polymer formulation, 9 months of work, violently snap at 312 degrees. The engineering spec demands stability at 350 degrees. The program is $2.4 million over budget, and the final launch vehicle integration window closes in exactly 11 weeks. Traditional chemical engineering operates on a trial and error loop. Tweak a monomer, mix, cure, test, and wait. That cycle consumes 9 to 12 months per iteration, time the engineer no longer has. The failure is rooted in a structural paradox. Rigid aromatic backbones provide exceptional heat resistance, but they destroy elongation, causing the material to shatter under physical stress. No current database contains a molecular combination that hits 350 degrees while maintaining flexibility. To solve this, the system must autonomously invent a material that does not yet exist. This maps the positioning of a specific AI architecture within the broader multi-agent ecosystem. Agent number 25, the scientific discovery agent, is engineered for abductive reasoning. It inherits capabilities from the parent framework, pulling sequence planning, memory, and verification into a closed-loop workflow. While standard large language models are graded against an answer key of established facts, Agent number 25 is built to propose testable claims that have never been verified. It is designed to be wrong on purpose. The operational pipeline follows a 5-step loop, moving from initial hypothesis formation through digital physics simulations, physical synthesis, and testing, before feeding back into model refinement. Red markers in this vulnerability matrix highlight severe failure modes. Restrictive data mining clauses and wet lab time lags can stall the loop. The cyan guardrails illustrate the required engineering workarounds, like enterprise licensing and Bayesian uncertainty management, to maintain operation while lab results are pending. By structurally anticipating its own potential for failure, this architecture is a deployed industrial standard. By early 2026, the AI material science market reached a $1.2 billion valuation, growing 25% annually. Google DeepMind's GNoME tool established the foundational layer for this market by identifying 380,000 stable crystal structures, making centuries of hypothetical discovery available to the public. Commercial entities under the Industrial Materials ADI and Computational Chemistry banners are now embedding these multi-agent discovery pipelines directly into the R&D divisions of global chemical manufacturers. Financial indicators show these platforms outscaling traditional methods. Schrödinger reported 2025 revenues exceeding $250 million, with their materials discovery division growing faster than their drug discovery segment. The aerospace engineer solves her hardware delay by plugging directly into this capitalized industrial ecosystem. The operation begins with the perceive phase, driven by the literature synthesis subagent. Using a fine-tuned Cybert encoder, the agent ingests over 12,000 published papers across polymer chemistry and aerospace engineering to map the boundaries of the domain. Hierarchical clustering with a 72% cosine similarity threshold forces this data into 47 distinct color-coded topical groups. To maintain stability, the architecture employs aggressive fault tolerance engineering. Rate limits and circuit breakers ensure that a single dead API cannot corrupt the synthesis map. The objective of ingesting 12,000 papers is to rigidly define the current limits of human knowledge on the subject. The knowledge gap agent scans these clusters to mathematically locate voids in the literature. This formula calculates the entropy of a given cluster, subtracting observed entropy from expected entropy. A gap score above the 0.35 threshold signals a significant opening for discovery. Purely statistical analysis is vulnerable to the streetlight effect, the tendency to prioritize data-rich, heavily published areas while ignoring novel gaps. A hard-coded guardrail prevents firing unless the gap exceeds 0.35 and the cluster holds 200 papers. The algorithm locates a massive void where block copolymer architecture meets aromatic monomers, an area with zero prior aerospace research. The gap registers at 0.41. These scientific gaps carry a high signal. The hypothesis agent uses abductive reasoning to propose a specific molecular structure for that empty space. This multi-objective Bayesian optimizer balances three weighted variables: explanatory adequacy, baseline plausibility, and novelty. Prior plausibility relies on a graph neural network trained on 500,000 polymers, ensuring inventions follow physical chemistry. Novelty uses inverse cosine similarity. The agent is rewarded for diverging from consensus, pushing to the furthest edges of material embeddings. The result is three novel candidate formulations, utilizing aromatic dianhydride diamine pairs in block architectures. Rewarding novelty via inverse similarity allows the agent to navigate 100 million monomer combinations and locate high-performance candidates on the Pareto frontier. A hypothesized molecule has zero value if it cannot be synthesized in a physical lab. The experimental design agent translates digital structures into a strict auto protocol, defining stoichiometry, temperature ramps, and the statistical power needed for characterization. A synthesizability gate immediately kills any formulation requiring uncharacterized reactivity or monomers costing over $200 per synthesis. 60% of candidates fail this evaluation. An autonomous agent's ability to invent is only useful when strictly gated by real-world testability and physical economics. The validated protocol moves to the bench, where autonomous systems like the Berkeley A Lab physically synthesize the samples. The initial physical batch misses the target glass transition temperature by 15% due to unexpected batch-to-batch variability. Tracing the dotted feedback loop on the schematic, sequential failures hit a threshold that forces the system to mathematically reweight its prior plausibility score, sharpening its logic for the next iteration. An agent's intelligence is measured by the velocity and precision of its self-correction. Exactly 14 weeks after the initial engineering failure, the system delivers a validated breakthrough. This dashboard tracks the efficiency of the loop. Across 3 physical iterations, the property prediction error dropped from 12% to 5%, yielding a 56.7% success rate. The autonomous pipeline costs roughly $42,000 per successful material, a fraction of the industry average. The final material hits the required 350-degree threshold while maintaining full elongation, saving the multi-million-dollar launch window. Agent number 25 ignores the safety of predicting the known. It weaponizes the negative space of human literature to manifest high-performance materials that simply did not exist before.